We'll start this segment with our demotivational poster, Apathy. No mountain seems too tall when you don't care about climbing it. We're going to talk about tolerances and fits in this lecture. Now, in modern manufacturing, we want parts to be interchangeable. In the old days, I don't know how long ago, but certainly 100, 200 years ago, things were custom, right? So things were machined by hand and were modified. Each part was modified until it fit and worked and performed its function. But that's not really acceptable anymore. In the era of mass manufacturing, parts need to be interchangeable. Things break. I've had several problems on my car that I've fixed, and it's as easy as going down to the junkyard, pulling off the part I need, and putting it on. Away we go again. So parts are interchangeable, which is very convenient for maintaining things. Also, it makes things cheaper if you manufacture a lot of one thing rather than custom manufacturing every single part. Further, parts can be made at many different locations this way. Now, in order that parts fit together, the size has to be close enough to fit and work, and that's part of tolerancing. So ideally, parts are identical, but the fact is they're really not. So we have to have some way of effective size control, and that's what tolerancing is all about. Now, if you try to make it too precise and too accurate and too close to the actual nominal size, whatever the print calls for, well, then it could get really expensive very fast. So dimensions have to be specified with the appropriate accuracy, enough to perform the function, but not too much. If you think about cutting a 2x4 for a house, do you really care if it's a 32nd of an inch too long? Probably not, or even too short. Right? There's a certain level of precision there that is appropriate. Anything more than that means it takes a lot more time and a lot more effort, and there's waste, right? What if you cut it a little too short? What if a 2x4 is a 32nd of an inch too short? Well, most of the time it doesn't matter, right? Worst case scenario, you can certainly shim something like that. So it's important that dimensions are specified with the appropriate level of tolerance. Obviously, the higher the accuracy, the smaller the tolerances, and the more time it takes to make the parts, the more waste there will be, because there will be parts that are made wrong. But the lower the accuracy, the larger the tolerances. Sometimes no tolerances are really required, and these are less expensive parts. Now, of course, the worst case scenario is you make a bunch of scrap, right? The parts have no tolerance, and so there's no real size control, and none of them work in the desired assembly. Of course, that's not desirable either. Now, there's size tolerancing for dimensions, but there's also surface finishes that are important. There was an episode I saw from a channel on YouTube. I can't remember the name of it. I'll try to post it for you. But Project Farm, that was it. He experiments with several different interesting things. He'll compare strengths of glues, super glues, bolts, materials. I think it was one episode he ran two mower engines, one with synthetic oil, one with regular oil, drained the oil, ran them until they failed to see which one would fail. You can go find that if you're interested. But anyway, it's an interesting channel. And in one particular case, he had I think it was after that episode with the lawnmowers, that it threw a rod out the side. And what that means is the connecting rod between the piston and the crankshaft snapped, it broke, and he decided to repair it with J.B. Weld. Now, I seriously doubt that it was his idea to do this. As a matter of fact, in the video, I believe he said that there were so many requests to do this, he went ahead and did it. And you could kind of tell he knew it wasn't going to work. I knew it wasn't going to hold together. It was obvious. J.B. Weld simply does not have the strength required. But it's not just the strength of the J.B. Weld that's not appropriate. When he repaired it, I noticed that some was on the inside of the connecting rod, on the journal, that has to connect to the, or ride on the crankshaft. I knew that wasn't going to work, because there's no way, filing by hand the way he did, that you could get the surface finish required so that the oil could provide a adequate lubrication between the connecting rod and the crankshaft. So I knew it was going to fly apart. Sure enough, it did. So the surface finish is also important in addition to sizing. Another thing that's important is the geometry, right? If you think about it, the connecting rod, where it connects to the pin on the crankshaft, both the pin and that connecting rod have to have a certain level of roundness, right? Their geometry has to be right. So anyway, so roughness is one of the pieces of the puzzle, and it's important for parts that have to mate together, that touch each other, or that are separated by an oil film. Now, the surface roughness is measured in micro inches, and I'll show you in a minute what that kind of looks like on a fine scale. But here's a a visual scale you can purchase that has examples of various finishes, and the process used to a large part determines how fine the surface finish can actually be that's achieved. And so you'll notice there's several different processes stamped into this. We've got all the way from profiled down to lapped, lapping being the procedure that produces the finest surface finish on this scale. And it goes, if you notice 500 ST, there's several different 500s. Those are all the same roughness, but produced by 3 different processes, and you can see the legend up in the corner. And then all the way down to the 8L, 4L, 2L, those are lapped finishes, which is the finest process shown here. So you can kind of see on this scale how fine the surface finish is. But what does it really look like? Well, if you look at it kind of from the side and on the micro scale, there's a couple of different things that you'll see. You'll see generally a waviness, a very fine waviness, but also an even finer roughness. And so what we're really interested in is less the waviness and more the roughness. Now you'd see surface flaws where there's a scratch, you'd see the waviness height, but what we're really interested in is the roughness itself. The waviness can be problematic as well, but for our definition purposes we're really looking at roughness. Now the typical surface finishes that can be produced by various processes are shown in your book as well. You've got anywhere from flame cutting, which is one of the roughest surface finish methods or techniques for producing surface finishes, but it does cut, all the way down to polishing, lapping, and super finishing that can produce surfaces that are finer and finer. Now obviously as you increase the surface fineness, the finish, reduce the level of roughness, you get into higher and higher costs. And here's a relative rough estimate chart of the increased cost in machining. Now the 100% mark is represented by a finish that's just a turn finish, so on a lathe, for example. Now as you go from there, that's typically a mill or a lathe can achieve a 63 micro-inch surface. Now it's easier, I think, with a lathe than with a mill, but CNC mills today are pretty good, so certainly you can produce this finish. As you increase, if that's 100% cost, as you increase the fineness of the surface finish, just going to grinding, you increase the finish by 240%. So that's the increase over it, right? That's not just the cost. So you're going to pay the 100% for the machining and then 240% of the machining cost in order to get to a surface finish that is twice as good as what you finished with after machining. So a 63 micro-inch is a typical as machined finish. If you go down to a 16 micro-inch, there's a 400% increase in cost. Now you might wonder, well, where do we need these sorts of things? Well, in the journal bearings that I mentioned earlier is one place, but also in dairy applications or food processing applications. The surfaces have to be very fine. If you think about dairy, it has a lot of biological things in it, or even any processing of many foods have a lot of biological elements in them, and if those biological elements become stuck in not a crack, but a rough area of the material, it can actually breed and cause spoilage of whatever food products go through afterwards. So there's all these different costs, and you can see, of course, if you don't need something to be machined, if it can simply be saw cut, right, then you can decrease the cost significantly. So it's worth keeping this chart in mind as you're deciding what surface finish. So just like tolerance, the lower quality surface finish we can accept, the lower the cost of the part is going to be. So you really need to know what surface finish is required for the application. Now a lot of times the surface finish requirement comes from experience, it comes from having worked on parts like this before, and most of the time if you go to work for a company, you're going to be producing same but different sorts of things. I mean, there are some companies that are ubiquitous. Yamaha comes to mind. They make keyboards and motorcycles. I mean, how different can that be, right? They make all sorts of things, but of course they have divisions of their company that specialize in different areas. I seriously doubt that the people designing pianos go over the next day and design motorcycles. So you're still going to be in an area where you're concentrating on one family of products at least, and typically you'll learn while you're there what level of surface finish is desirable for a particular application. So if we're going to have interchangeable parts, we need some way of guaranteeing that the fit is proper between those parts. One type of fit that's commonly desired is what's called a clearance fit, where it's guaranteed that the biggest part will always fit inside the smallest hole. So Typically we're talking about round things, shafts and hubs, and so it's generally roundish parts where we're particularly concerned, because a lot of time the type of motion that we have is a rotational motion of two parts, one with respect to the other. So clearance fits are a class of fits that are made or defined so that you get a similar fit. If you think about it, a thousandth of an inch of clearance on small parts is a different fit than a thousandth of an inch of clearance on parts that are, say, 10 inches in diameter. It's a very different fit. The fits are much tighter when you have a bigger, I know that doesn't make sense because it's still the same thousandth of an inch of difference, but relative to the part size, the clearance needs to adjust. And there's a table on page 492. Of course, you can get these out of Machinery's Handbook as well. And I believe they have an RC2, an RC5, and an RC8. RC stands for running clearance, and it just means that the parts are meant to move relative to one another. But there's a beginning bit of information for what size of tolerance is required in order to get a particular class of fit. On that same page, or maybe the preceding page, there's a description of all the RC1 through RC9 fits and what they would typically be used for. Now here's another example out of the book. There's more of these in Machinery's Handbook, but this is similar information. You can see the RC2, 5, and 8 listed here, and these are clearance holes. They use what's called the basic hole system. What that means is that the hole could potentially take on the nominal size. Let's say you have a 2-inch nominal shaft. Okay, shaft is nominal 2-inch diameters. Hole is nominal 2-inch diameter, but of course the shaft's going to be undersized a little bit, and the hole might actually be 2 inches. There's some tolerance, so as the size gets larger, then the tolerance gets larger. But this particular chart would be for one particular size, and I think it is actually a 2-inch size. Now it's actually a range, and 2 inches falls into a particular range, but you can see the range on the table that I just pointed out. What was that, 13.3? So if you have a 2-inch size and you have an RC2 fit, you can see graphically what the fit is like. How big is the tolerance zone? So the bars above 0 are all tolerances on the hole. So the basic size would be 0 off. It'd be exactly on at 2 inches. But with an RC2, we could go up. You can see that bar extends to somewhere under a thousandth of an inch, about a half thousandth or so over would be allowed for the hole. The shaft, on the other hand, could never take on the 2-inch side. Remember, this is a clearance fit, so you must guarantee clearance between the hole and the shaft. The shaft has to be undersized a little bit. And you can see that. And it looks like the shaft is undersized by maybe a third of a thousandth or so, something like that. But the maximum undersize of the shaft would be about a thousandth under. And that you can see that represented by the G5 capital H6 pair. Now the G5 and the H6 are tolerances that are they're definitions that are commonly used in the metric system. In the jobs I've had, I haven't seen a lot of people use those. Some engineers will try to include them on the drawing, but most machinists, in my experience, don't have experience with these and don't know what they mean exactly. They always have to go and look them up. I typically would always just put the dimension and the tolerance, plus minus tolerance, on my drawings, or whatever was appropriate. That way the machinist didn't have to go and look anything up. Like I said, most of the machinists I knew didn't have these memorized. Now, maybe it's different in other companies, I don't know. But to me it was just more convenient to give the machinist the actual size range that I could accept, depending on what the process was. Maybe an upper and lower dimension, or maybe a dimension, nominal dimension, so they knew what I was shooting for, and then a plus minus tolerance. Now you'll notice that as the running class gets higher, now this is not for a different size shaft, this is just for a looser fit around that, say, 2-inch nominal shaft diameter. All the way over on an RC9, there's a lot more clearance guaranteed between the shaft and the hole. And so the fit is a lot looser on these. As a matter of fact, when I was in college, I took a class where I had to make some parts, and unfortunately I can't demonstrate these perfectly. Forgot to get them out. I'll try to demonstrate them on video. But I made 3 separate parts, and they just basically look like this. So they're just a part that's machined, a shaft that's machined out of just some rod stock, and I've got 3 of them here, and I tried to make them to a very particular size. I don't remember what the clearances were on these, but this is the inner race from a ball bearing. And if you know anything about ball bearings, their sizes and the tolerances are very tight, so their sizes are very closely controlled. So this was a good hub or ring to try on these various shafts. And so if I put this one on, you can see I'm struggling a bit to even get it to go on. But once I get it on, I don't think you can hear it. There's just a very little bit of play. I'm toggling it back and forth as much as I can, and there's really not much motion. Now these others I tried to make more loose. So you should be able to hear that. The microphone should be picking that up. There's a lot more play on this one. I made this more undersized. This would be closer to an RC9. Now I don't, like I said, obviously these are all running clearances. I don't have a micrometer here, so I can't tell you what the size is or how much the tolerance band is, but that was a lot looser than the first one. And normally when we're in class, I pass these around. Now here, you can hear that too. Now that feels like a little bit less clearance. I can't move it quite as far. The camera can't pick up the angle, the deflection angle, but there's less deflection on that one than there was on this one. Yeah, this is certainly the loosest, and you can feel it. You can really feel the difference in the clearance in all three of those, even though I know that these are not like an RC1 and RC9. They're more in the middle of the range. I know I didn't do like an RC456. I think it was an RC258, something like that. But it was really interesting. Another thing, kind of a funny story here, this is supposed to be what's called a popper. It has a female hole here and a shaft here, and what's supposed to happen is you put it together, and when you pull it apart, it's supposed to pop. Of course, there was no pop there. I didn't edit anything out. Again, this was the same class I was making these, and I was trying to make them very, very precise. That was the challenge for the lab. And so I was measuring this thing constantly, made sure the lathe was set up really well and perfectly, well, not perfectly, nothing's perfect, but as straight as I could get it, and make this surface very tightly controlled. So the dimension here and here would be the same, geometrically, and also I think there was supposed to be a thousandth or a half thousandth of clearance between this shaft and this hole. Of course, me being an inexperienced machinist, it was quite a challenge for me. So I finished making this, I pulled it apart, and no pop. And I was so disappointed, and the professor came over and he measured it carefully, and he said, well, it should pop, you're within the tolerance. And here's the embarrassing part. It took the graduate TA to come over and say, oh yeah, it's not going to pop. You got a hole all the way through that thing. So I accidentally picked up a piece of stock that had already been drilled and worked fine for what I was doing, so I just went ahead and worked it. So if you cover up the hole on the back side, it pops nicely. You just have to maintain the air pressure in the darn thing. So we probably spent a good 30 minutes trying to figure out what the heck was going on there and why they wouldn't pop. As a matter of fact, you may have noticed that it's a little bit difficult to get these together and apart, and that's because there is such a close fit between the two. Now this is, I think, finer than an RC1. Well, it may be an RC1. Looks like it's about a third of a thousandth. That would be within tolerance. But then again, this size chart is for a higher size. Yeah, this is probably about an RC1. So that's a pretty tight fit, but there is still clearance between the shaft and the hole. Now, moving from fits where there's guaranteed to be clearance between the mating parts, transition fits are fits where there may be interference between the two. In other words, the shaft may actually be larger than the hole, or there may be clearance. The tolerance range is set up so that often there can be interference between the mating parts. Now, where would you use this? Well, these are typically used, they're also called location fits. So these are typically used where two parts need to be located with respect to each other very precisely. So if you've ever rebuilt the engine in a car, you've probably had dowel pins or some alignment thing that align the cylinder head to the block. That is typically a transition fit, and the reason for it being so tight is you really want the head in just the right place on the engine. Now, sometimes it's not really necessary, but often that's one place where these are used. Interference fits, on the other hand, are fits where it's guaranteed that the hole will be smaller than the shaft. So there will always be some material interference between the shaft and the hole because the shaft is simply guaranteed to always be bigger than the hole. And so what happens is, it's a challenge to get the two together. Sometimes you can press them together. Sometimes you have to use other methods of getting them together. But often heating up the hole and cooling the shaft is used to get the two parts together. I had an example. There was it's one of my Saab stories. I say that because it was an engine I rebuilt in a Saab 9-3. I think it was a model 98 or 99, something like that. Anyway, I guess the previous owner didn't know that you had to change oil in engines, and so I just bought the thing, and I had changed the oil in it, and I drove it for several thousand miles, and it seemed to be okay. And one day I was, of course, going on vacation in this car, and it broke down on me. Well, towed it home, got the engine apart, looked at it, and got the valve cover off, and there was just dried oil caked everywhere. It was awful. You could tell immediately what was wrong. It turned out that in four-cylinder engines, there are these things called balance shafts, and the balance shafts, well, theoretically, you can't eliminate all the shaking forces essentially from slinging the pistons up and down in the cylinders, and so there are balance shafts that are offset weights that rotate and are supposed to cancel out the shaking of the engine so that you just feel like the engine is a smoother running, better engine. It's really, I mean, yeah, you could say that it's there for preventing the engine from shaking so much, reducing vibration, maybe increasing the life of the components. I really didn't tell a difference. You see, what happened was these balance chains, or balance shafts, were driven off of chains, and the chains were literally a little bit smaller than a bicycle chain. I was just flabbergasted that they would run a component like this with such a small chain. As a matter of fact, that was known to be a common problem in these engines, is that the balance shafts would lock up and you'd mess up the engine. Well, anyway, it ended up, that's what had happened. The chains then broke, which caused, I've forgotten what happened. I think it broke something else, and then it rotated a bearing on the crankshaft. And anyway, so I got the balance shafts out, and there was a bearing that was supposed to be in the balance shaft, and the bearing was only supposed to be an inch wide. So it's a round thing. It was probably 2.5 inches in diameter, something like that. And it was supposed to be about an inch wide. Well, the balance shafts on the journals had rubbed on this bearing surface so much, this bearing piece, which was supposed to be about a 1/16 of an inch thicker. So it had rubbed on it so much that it had extended the length of that bearing out to about 3 inches. It was ridiculous. I'd never seen such a thing. I was amazed the engine had not locked up before then. So I decided I was going to eliminate the balance shafts. I pulled them out. I got really lucky. I found some tubing or pipe or something that fit almost perfectly inside of that area where the bearing went. I took the bearing out and put this in, and I knew that I needed to put something in there to block the oil way. Because if I didn't, then the oil that's supposed to lubricate that bearing would just leak out there, and the engine wouldn't have significant oil pressure to keep it from locking up again. So I rebuilt the whole thing, got it all together, and it worked. I was amazed. I put some anaerobic sealant in there. Obviously had good oil pressure. I could tell from the way the engine was running and the gauge and so forth. It worked great. Got it all together. I was so excited. It's that moment. If you've ever rebuilt an engine, you know what it's like. You get the engine all done. You get it back in the car, and you turn the key half hoping you didn't leave a screwdriver in a piston or something, okay? You're really thinking, did I do everything to make sure this is going to work? Because it's a lot of work. In fact, that car is where I realized that for a front-wheel drive car, you have to lower the subframe out of it, and you lower down the engine and transmission. It's just the best way to get the engine out. Sometimes the only way. In that process, you got to take the front wheels off. And so I got it all together, got the wheels on, and the engine ran. I was so relieved. I went ahead and let it down off the jacks and decided to drive it around. It did great. Well, there's a thing about the front wheels on that car. It turns out that the front wheels use a bearing on a hub, and it's a split bearing. And so what that really means is that the outer race is split and has to be pressed together. It's pressed into a housing so it stays together. But to keep it all together, the pressing is not made to hold it together. There is an interference fit, but it's not enough to hold it all together. You have to tighten down the nuts on the end of the drive shaft. Guess who forgot to tighten down those nuts? Right here. I completely forgot. I mean, I had them hand tight, so it worked, and the bearings worked fine. About a week later, the person who was driving it said, this thing's making a funny noise. I don't know what's going on. Every time I turn a corner, it just sounds like sandpaper grinding or something. So I checked into it, and of course, I had destroyed the bearings because I completely forgot to torque down the nut to the required specification, and I hadn't really torqued it at all, really. It was pretty much finger tight. I think I may have put a wrench on it and did a little bit. So it ended up that I needed to take this split bearing, because basically what had happened is the outer two races had been able to separate, and so that just destroyed the front bearings. And it turned out the way they had designed that, the hub for the wheel also had to be pressed into the inner race for that bearing. So I took it to work. At the time I had access to a hydraulic press, and I tried to press the hub out of the inner race of the bearing. That was one of the most difficult fits I've ever seen. I pushed and pushed on that thing. I thought I was going to break the hydraulic press. When it finally gave and the hub came out, it sounded like a shotgun going off. I was so glad I'd done it after hours, after everyone had left, because, well, except of course the office staff. There's no one back in the assembly area. And I mean, this thing came apart, and I thought it was going to shoot across the room. It was such a violent disassembly. But it worked. I got the whole thing back together, and I actually managed to, screw the nuts on the end of the drive shafts this time, and it was in good shape then. The engine ran great for about 6 months. It wasn't my fault. That car was totaled. So that's the end of my sob story. It was the person driving it ended up rear-ending someone, totaled the car. Fortunately, the thing had airbags and the passengers were all fine, so that was good. Accidents happen. So that's kind of my sob story. Anyway, the whole point is that when I went to put the hub back together with a new bearing, I actually froze the hub and I heated the bearing so that they were much easier to slip together, because I was really worried that if I had to apply so much force to get the two together as I did to get the two apart before, the old parts, that I would just have, it would be practically impossible. I'd get it in cockeyed and push it in and damage one or the other. So heating is often used to expand the hole, and cooling is often used to shrink the shaft part, and it's usually enough to get the two together. In fact, in my case, it was enough to slip them together quickly, and once they came to thermal equilibrium, they were set. It was done. Unfortunately, I didn't have to try to take it out again. But there's another table you need to look up. Page 495, table 13.4, has a bunch of what's called force fits or interference fits. And of course, there are tighter and tighter force fits with more and more interference that, I don't know what the rating was. I should have measured it. I probably did. I don't remember what it was now. But anyway, there are harder and harder press fits. There was another press fit I tried. It was a shaft coming off of a mower engine. This was about 11 horsepower mower engine, so I think the shaft was about 1 inch in diameter, and I wanted to get a cast iron pulley onto it. Turns out the mower had some trouble. I'd bought it to rebuild, and it didn't have a pulley on the engine, so I went down to the local hardware store and bought a cast iron pulley because it was the cheapest one. Well, I'll tell you more about that later and what happened, because that's my story for another slide. Anyway, there was an interference fit, and I messed something up there too. So the amount of temperature change required in order to change size significantly depends on a lot of things. It depends on the coefficient of thermal expansion primarily. Of course, the more change you cause in the temperature of the part, the more the dimensions change. So usually, for practical purposes, it's pretty easy to take apart like that bearing I was talking about and just put it in a common oven, something you'd use for baking. Take the temperature up several hundred degrees, and the size will change enough that it'll make a big difference in assembling. And even taking the male part, the shaft, and put it in the freezer can make a huge difference in its size as well, and give you more clearance, so that even a force fit fits together like a clearance fit. And of course, you got to put them together quickly, because then they come to thermal equilibrium quickly, because they're transferring heat very rapidly since they're in contact. And one shrinks onto the other. But to calculate how much temperature change is needed, here's our equation for deformation, how much the size would change. So it depends on what's called the coefficient of thermal expansion, that's CTE, and there is a page in your book you need to mark. It's page 496, table 13.5. We'll mark this page for other purposes later as well, but that's where you'll find coefficients of thermal expansion. L is the initial dimension, whether it be a diameter or length, whatever it is you're trying to fit together. Delta T is the temperature difference between the initial and the final state. So between the normal room temperature usually versus heated up or cooled down temperature. And so you can figure out how much deformation you need to accomplish given the force fit and how much interference there is. You're trying to erase all that interference basically, plus usually provide a little bit of clearance so you can get the two parts together. But from that, and knowing the material's coefficient of thermal expansion, you can figure out how much temperature change is required for one or both of the parts. And I'd like to talk about this a little more, really outside of the context of tolerancing and parts fitting together. Coefficients of thermal expansion is one of two topics that I feel are commonly not addressed well enough in most engineering programs. And they are critical. They are very important to understand. If just about everything we have in our advanced civilization are assemblies of things, right? I mean, if you think about your cell phone, you think about the microphone I'm using to record this, you think about your car, your house. everything, even a concrete slab, is an assembly of multiple components. For example, you commonly have rebar in concrete, especially if it's reinforced. Of course, in concrete there's multiple things anyway. You've got usually gravel, sand, and other things. Anyway, the point is, you usually mix multiple materials together, and the coefficient of thermal expansion is really important to understand. You can find tables of coefficients of thermal expansion, and anytime you make an assembly, you should always have some idea of what's known as CTE, what the CTEs of things are, so that you know whether or not they'll fit together. One of the reasons that steel is used as a reinforcing element in concrete is because steel and concrete have very close coefficients of thermal expansion. If they didn't, what would happen? Let's say that the steel didn't hardly stretch at all with temperature and the concrete does. What would happen is the steel would literally pull through the concrete. It would release its connection to the concrete. If you've ever poured concrete or you've worked with rebar, you know that rebar has ridges on it. And the reason it has ridges is so that it can interface with the concrete and tie to the concrete. And if there was a significantly different coefficient of thermal expansion between those two materials, those little ridges wouldn't do much. One would give. Either the steel or the concrete would absolutely give as temperature changes. And there's nothing you can do about it. The stresses generated when the temperature of things change and some geometry is trying to prevent that change are just ridiculously high. Good luck keeping things together. So CTE is very important because you try to match the coefficient of thermal expansion of materials that are assembled together so that when the temperature changes they don't pull apart and break your assembly. So something to be aware of for sure as we talk about all this. But in our context we're really thinking about force fits and how you might get something to fit together when really there's interference between the two. Another one of my failures, seems like I've learned a lot from failure, but I have a boiler system. I heat my house with wood, and one of the inconvenient things is that the boiler really runs best when it runs hot, so you really want to put a bunch of wood in it, burn it all. Well, really that's too much to heat my home. I would cook myself in my home if I put all that heat into my home at once. I would rather set some of that aside. So I have a system for doing that. I have a couple of propane tanks that don't hold propane, they hold water, and basically what I do is I let the boiler run, heat up that water, and I use that water to keep my house warm. Well, along the way I had to bury those tanks. I decided to bury them because there wasn't going to be propane in them anyway. There's no way to add propane to them, so it was safe. It was just going to be water. And so I insulated the tanks, dug out a deep hole with my backhoe, set them in place, and I needed to connect piping to them to pump water in and out of them, or really through them, because you really don't want air or anything in there, so you want it filled with liquid. So I ran piping to it, and of course the threads on the tank are all steel, because it's an all-steel tank. And so I knew better than to take male metal threads and run them into female plastic threads, because of course as you drive in the metal threads, it's much stronger than the plastic. If you over tighten it, the female plastic threads can break, right? They can open up. And another thing that happens is that as you warm up this joint of metal threads and female threads, they will expand some. And so I thought, well, no big deal. I'll make sure, since I've got all female metal threads in the tank, I'll just run plastic threads in, tighten it up real good, and it'll be fine. And I did that. I pressure tested it really well to make sure it would work, and there were no leaks. Everything was going great. Even, had the tanks exposed, so I was spraying soapy water around all the joints to look for any air bubbles, and no leaks at all. It was great. I pressurized them up to, I think, maybe 100 psi or so. And to do it safely, I filled the tanks almost completely full with water, so the amount of compressed air wasn't very large. It was just a little bit of compressed air above it. So if something ruptured, there wasn't much air to expand, and it wouldn't be like a bomb of a 500-gallon tank going off, And everything was great, and I thought, okay, well, I've done everything I can. Is there any reason I need to leave this pit exposed? And winter was coming, and I needed to get this system going. I thought, well, yeah, I should probably leave it exposed so that if something happens, I can get down and fix it. And then I thought, what's going to go wrong? I've done everything. I've pressure tested everything, so I'm just going to cover it. So I did. Backfilled it all with dirt, had all my piping and everything, and thought everything would be great. And so, cranked up the boiler, was getting nice heat out of it. I was able to put it in the tank, seemed to be working great. And all of a sudden, a week or two later, I realized that the tanks just weren't holding as much thermal energy, or what you'd probably call heat, as they should. I thought, what on earth is going on? So I did some very careful measurements, and I'd already calculated how quickly those tanks should lose heat, given that the ground temperature is about 50 degrees, and I had put insulation around the tanks. And I thought, what on earth is going on? They're losing heat at a rate that's, I've forgotten if it was 10 or 100. I think it was 100 times what I'd calculated. And I thought, well, is my model off? Did I make a mistake in the math? What on earth is going on? Finally, one day I was listening, because they're right outside of a wall in my basement, and I heard leaking. And I thought, what on earth? Why are these tanks leaking? Of course, it ended up they were leaking. I had to dig out very carefully to get down to these darn tanks again, get down to the connections, find out what was going on. What had happened is the boiler, or the water in those tanks, went from about 50 degrees to about 200 degrees because of the boiler heating up the tank. Guess what happened? Well, CTE bit me. So what happened is both the male and the female threads, remember the female threads are steel, the male threads are plastic, they both expanded, and that was fine. As long as we went up to 200 degrees, they both expanded. Actually, it turns out the CTE of plastic is larger than the CTE of steel. So the plastic was trying to expand more than the steel, but the steel wouldn't let it. So at 200 degrees, that was fine. The problem came in when it cooled down, because now the plastic has been deformed. And so as it cooled down, the plastic shrunk a lot more than the steel did, and sure enough, I got leaks. So I had to dig the thing up the next summer, put something that had a closer coefficient of thermal expansion in, and then transition to I actually did end up transitioning to a plastic pipe. I originally used CPVC. It's a type of PVC. I used Schedule 80, so it had a nice thick wall. That didn't work. I transitioned to something called PEX. It's polyethylene tubing that's been expanded. You might say, well, you're going to have the same problem because you somewhere have a plastic to metal connection. Actually, in this case, I didn't, because the male portion was more of a barb, and the female portion was just the PEX hose, which you put in place, and then you use a metal ring to clamp it in place. So because of the way they're designed, and they're designed for taking high temperatures, I haven't had any trouble with leaking, and now everything works as it should. But just another little story to hopefully I convince you throughout all these things that the first prototype never works right. Leave yourself some space for error. Okay, in my mind, I knew I should not have backfilled that. I just knew. I should have thought, I've got insulation on the tanks, I'll lose a little bit of heat, it won't be the end of the world. If there's a problem, I can easily get down and fix it. Well, that was I learned my lesson, I hope. So another thing, you should always leave clearance between parts. If you plan to have parts made so tightly so that they'll, such nice tight tolerances that fit together perfectly, that's a bad idea. Learn to tolerance well and leave yourself some clearance, and leave yourself some clearance in your designs and fixing things too. Now, when parts fit together and there's stress during the force fit, the amount of stress is important. Remember the pulley I was telling you about, the cast iron pulley that I put onto the shaft of the engine? Well, of course, I was working on the thing, and when I'm working on things, I have to confess, I tend to get a little more upset than I should. And I'm trying to get something done, because typically I need to use the piece of equipment for something. At that time, I probably needed to cut my grass, and so I was trying to make this not concrete, but it's brittle, this iron pulley, cast iron pulley, fit onto a steel shaft. Well, I didn't realize that pulley had been there was a hole in it, but it really hadn't been bored to the proper size. It was close, but it was a few thousandth under. So I think I actually measured it, and I think it was about .998 or something like that. And the shaft was maybe right on 1 inch or just barely under. So there was enough interference that I thought, okay, no big deal, I'll just drive it on. Well, if you know anything about cast iron, you know that it's a brittle material, and like most brittle materials, cast iron is better in compression than it is in tension. So imagine a hub that I'm trying to push onto a shaft. What am I doing? Well, I'm trying to expand it, aren't I? Well, that was problematic. So of course I've grabbed my hammer and I'm trying to tap the thing on, and eventually it starts moving because I've got some oil on the shaft, and I'm tapping and tapping away, and of course it's not moving, so I get a bigger hammer, right? And I'm tapping and eventually hitting the thing. I got it on, but the hub cracked. So of course I had to go get a different material, and I said to heck with it. I went and got a hub that you could weld a pulley onto, and it was a little more expensive, but it was worth it. And then it worked fine because that was steel and it was actually already made to the correct size. So sometimes the stress of a force fit can be so great that the outer member cracks. And so we want to calculate how much stress there would be after the assembly is done, because I could have taken that cast iron pulley, and it would have been a lot smarter to just settle down, go get myself some iced tea and cool down, and heat up the pulley in my oven, right? Hey, take it up to 500, 550 degrees, whatever my oven can reach. grab it with a hot mitt and just slip it on, right? But I wasn't thinking. I was upset and trying to get things done. But even if I had done that, it would probably still crack. I don't think it was the hammer blows, believe it or not, that actually caused it to break. I think that the shaft went into the hub so far, eventually the hub just failed. And so to calculate the pressure at the interface between the hub and the shaft, there's an equation here. It's on page 496 and 497. There's even a procedure for dealing with all this, and all these equations will be there. Now, one thing that confuses students about this is the graphic. Let's start there. I was using the example of a solid shaft coming out of an engine from a mower and a hub on a cast iron pulley. Now, you can imagine the hub. It's just a ring. You can neglect the outer portion, the pulley itself, the spokes, and so forth, and just focus in on the hub. Well, that kind of makes sense. The dimension from B to C would all be hub. But this procedure is flexible enough to deal with a shaft that is solid or a shaft that is hollow. And what you see here from A to B is a shaft that is hollow at dimension A. Okay, so the shaft itself is from A to B, and then there's a hole in it, right? Now, some shafts are solid, like the shaft I was dealing with. So the dimension A, in my case, would have been exactly 0. So in all these equations, if you have a solid shaft, make A equal to 0. And in fact, this confuses students so much, I highly recommend you write two things. There's I think it's page 497, or, well, it may be 496. Maybe it's 496 where this figure appears. But on that page, make yourself a note and highlight it that says A equals 0 for solid shafts. Also do this. Students confuse this all the time, and you will lose a couple of points on the first exam if you mess this up. A, B, C are all radii. They are not diameters. I commonly give a problem that includes diameters to see if you do this right. Now, it turns out that it won't matter if you think of A, B, and C as diameters or radii in the square bracket portion of most of these equations. It turns out that the dimension cancels out, except notice you've got that B in the denominator outside of the square brackets, and that's where it's really important. So you can kind of get by with using A, B, and C as diameters, but for that one term, you have to use radius. So make yourself a note that A, B, and C are all radii, not diameters in these equations. Another thing, this particular equation is the first equation that appears in that procedure section. Make yourself a note too, or highlight the section where your author says that this is only good when you have the same materials for the hub as you have for the shaft. So A to B is the shaft, B to C is the hub. When those two materials are the same, then you can use this equation. Now, really, you can get away with using this equation as long as the two materials have the same elastic modulus and the same Poisson's ratio. Okay, but they need to be the same. Okay. And that's why generally we use this equation just for the same materials. If the materials are not the same, then the equation becomes a little more complicated, where you have Poisson's ratio. You see nu 0 and nu I in the equation, and the elastic moduli E, O, and EI. Now, what is the O and I for? Well, O is the outer or the hub portion. I is the inner or the shaft. You might make a note of that. I goes with the material from A to B, and O goes with the material from B to C. Okay, so this is the equation you use when the material properties are different. Like in my case, right, I have the solid steel shaft, so I need to use the elastic moduli EI and Poisson's ratio nu I for steel, right, and then E sub O and nu sub O would be for cast iron in my case, since that's the outer or the hub component. So what these equations do is they allow you to calculate the pressure at the interface between the shaft and the hub. Now, that's not what I said before, right? I said I'd like to calculate the stress within the shaft and the hub. Well, here are two equations for calculating the maximum stress, and notice these would be normal stresses. Obviously, in the outer member, we're talking about a tensile stress. In the inner member, we're talking about a compressive stress, and that's why we've got this negative sign on sigma sub I, right, because that's for the inner, the shaft portion. But you use the pressure that you've calculated either from the equation for same materials or this equation from different materials. Use that pressure in this calculation in order to calculate the stress. Now, for the sake of exams, you are welcome to set up these equations in a spreadsheet, so all you have to do is type in all the different parameters and you're done. Now there's one parameter I haven't really talked about much yet. I kind of flew over it. That's the delta parameter. This one confuses students a lot because they look at the delta equation from thermal expansion. Delta equals, how is it, CTE, or I think we use epsilon, L delta T, and they think these two deltas are the same. They are not. Make yourself a note that this delta is the amount of interference. It's the total interference for the force fit, okay? You really need to know that, because a lot of times in the problem I tell you that I'm going to cool up or heat up, cool down or heat up the materials to get them together, and so students calculate the deflection there and then plug it right into this equation. That's not what you should do. You should use the interference amount in this equation for pressure, and then you'll calculate the pressure appropriately and you can get your stresses, okay? Be careful about all that. Please make all those notes. I'm serious, it will help you a lot. Now, if you're interested in the actual amount that the outer member stretches and the inner member is compressed, because they have to change size some, then these two equations allow you to calculate it. Now, understand that depending on the geometry and what the material properties are, the outer member may be the thing that stretches the most, or the inner member may be the thing that's compressed the most. Imagine having rubber, okay, as the shaft, and steel for the collar. In that case, obviously the rubber is going to be the thing that gives the most, right? There won't be hardly any stress in the steel. All the deflection and stress would be in the rubber, because rubber is like a weak spring, right, by comparison to steel. So here's a couple of equations for calculating exactly how much each member changes size. Because obviously if the shaft is bigger than the hole, it's going to have to come down some, and the hole is going to have to get bigger some. Well, how much bigger does the hole get and how much smaller does the shaft get? That's what these two equations answer.